Introduction. The science is typically cumulative, i.e., build up more powerful tools to perform more accurate measurements, need better, and are extended concepts of theory, and so on. While paradigms can change, research usually evolves based on past performance, which constitutes the foundation for further development. The scientist will be safer in their research and more prepared for new challenges if you know how your particular issue has evolved historically, what the greatest difficulties, the solutions, and the outstanding problems. In the more traditional sciences, philosophy, mathematics, physics, biology, etc., there is always a study's history along with much other dedicated to thinkers, inventors, and conquerors first, second, or third magnitude, as well as numerous monographs. In the case of computing, it is necessary to appear works as the basis and reference for students, new researchers, and those interested in the theoretical aspects that are behind this technology that dominates daily life this weekend and early millennia. The computer history is marked by sudden interruptions, by unexpected and unforeseen changes, making it difficult to view the evolution of computers by a simple linear list of inventions, names, dates. The desire to know the links that the work of individual men settled in time is accompanied by the urge to understand the weight of these acts throughout the history of computing. Seek an understanding of the facts through the events that preceded it is one of the primary objectives that will be present in this study, the history of computing. Computer science is a body of knowledge consisting of a conceptual infrastructure and technological building where to materialize the hardware and software. The first founded the second and preceded. The theory of computation has its independent development, in large part, technology. This theory is based on the definition and construction of abstract machines and power of the study of these machines in troubleshooting. The emphasis of this book is that theoretical dimension, trying to show how men through the ages have sought to develop effective methods for solving different types of problems. The constant concern to minimize repetitive and tedious effort produced the development of machines that began to replace men in certain tasks. Among these is the computer, which has expanded rapidly filled and modern spaces in which people circulate. From the appearance of the notion of natural number, through arithmetical notation and the more bound notation to algebraic calculation, it is shown as they appeared fixed rules that allowed computing quickly and accurately, saving, as he said, Leibniz, the spirit and the imagination. Descartes believed in the systematic use of algebra as a powerful and universal method to solve all problems. This belief has joined the other, and is the first ideas on universal machines, able to solve all the problems. It was a powerful belief mind who left respectable works in mathematics and sciences in general. Chapter 1. Alan Matheson Turing, the Cradle of Computing. The computer revolution began effectively to be held in 1935, on a summer afternoon in England, when Alan Matheson Turing, 1912 to 1954, a student of King's College, Cambridge, during a course taught by mathematician Max Newman, took note of Hilbert. Meanwhile, as was briefly mentioned in the previous item, a part of the mathematical community was seeking a new kind of logical calculus, which could, among other things, put in a sustained mathematical basis, heuristic concept, that is, to carry out a calculation. The result of this research was fundamental to the development of mathematics. It was whether it is possible to have an efficient procedure to solve all the problems of a particular class that was well defined. All these efforts eventually formed the theoretical foundation of what came to be called computer science. The results of Gödel and Turing motivated decision problem first try to characterize exactly which functions are capable of being computed. In 1936, Turing was acclaimed as one of the greatest mathematicians of his time, when he foresee his colleagues that you can perform computational operations on the theory of numbers through a machine that has built the rules of a formal system. Turing defined a theoretical machine that has become a key concept within the theory of computation. He emphasized from the beginning that such mechanisms could be built, and its discovery is just opening a new perspective to the effort to formalize mathematics, and at the same time strongly marked the history of computing. The genial perception of Turing was the replacement of the intuitive notion of an effective procedure for a formal idea, mathematics. The result was the construction of a mathematical concept of algorithm notion, a notion that he modeled building on the steps that a human being is when performing a particular calculation or computation. It formalized the concept of algorithm. The Turing Machine. One of the first models of the abstract machine was Turing Machine. As Turing himself wrote, computing is written symbols on paper. Assume that the paper is a grid. The flatness can be ignored, and it is not essential. Suppose the number of symbols is finite. The computer behavior is determined by the symbols which he notes at one point, and his mental state at that time. Suppose there is a maximum number of symbols or squares that he can watch every moment. To observe more successive operations are required. Let us assume a finite number of mental states. Let's imagine that the actions taken by the computer will be divided into such elementary operations that are indivisible. Each action consists of changing the computer system and paper. The state of the system is given by the symbols on paper, the symbols observed by the computer, and your mental state. Every operation, no more than a symbol, is changed, and only the observed change. Besides changing symbols, operations must change the focus of observation, and it is reasonable that this change should be made for symbols located at a fixed distance of the above. Some of these operations involve mental state changes the computer, and then determine what the next action. Turing's work was documented in On Computable Numbers with an application to the Einschätzungsproblem, published in 1936. He described in mathematically precise terms how powerful it can be an automatic formal system with very simple rules of operation. Turing determined that mental calculations consist of operations to transform numbers into a series of intermediate states, progressing from one to another according to a fixed set of rules, until an answer is found. Sometimes it is using paper and pencil, not to lose the status of our calculations. The mathematics rules require stricter definitions than those described in metaphysical discussions about the states of the human mind, and he focused on the definition of these states so that they were clear and unambiguous, that such definitions could be used to command the machine operations. Turing began with a precise description of a formal system in the form of instructions table that specify the moves to be made for any possible configuration of states in the system, then proved that the steps of a formal axiomatic system similar to logic and machine states, which make the movements in an automatic formal system, are equivalent to each other. These concepts are all underlying the current technology of digital computers, whose construction became possible a decade after the publication of the English mathematician. An automatic formal system is a physical device that automatically handles the symbols of a formal system by its rules. The theoretical Turing machine establishes both an example of his theory of computation as evidence that certain types of computing machines could be built. Actually, a universal Turing machine, except for speed, which depends on the hardware, can emulate any current computer, from supercomputers to personal computers, with their complex structures, powerful computing capabilities, since no matter the time spent. He proved that for any formal system exists a Turing machine that can be programmed to emulate it. Or, in other words, for any well-defined computational procedure, a universal Turing machine can simulate a mechanical process to perform such procedures. From a theoretical point of view, the importance of Turing machine is the fact that it is a formal mathematical object. Through it the first time, it gave a good definition of what it means to compute something. And this raises the question of what can be accurately computed with such mathematical device, subject outside the scope of this work, and entering the field of computational complexity. Chapter 2. The Ace Computer and Artificial Intelligence. Turing was sent to America to exchange information with the U.S. intelligence and know the projects related to computers. It took note of the emerging electronic technologies and even participate in another secret project, Delilah. A vocoder, known in movie espionage as scramblers, entered into contact with von Neumann, who wanted to bring him to join them in their projects, and the engineers of Bell, including Claude Shannon. Back to England, he joined the National Physical Laboratory, where he worked on the development of the Automatic Computing Engine, ACE, one of the first attempts to build a digital computer. At the end of the war, already held the knowledge of new electronic technologies that could be used to increase the speed of the then existing logic circuits. The real possibility of constructing models of universal Turing machines caused the British government to invest in the construction of this new device, but the Americans were more aggressive in their investments and ended up winning the race to build computers. Turing, a victim of political intrigue, was out of the center and control of new jobs. Its technical reports on hardware designs and software ACE were ambitious, and the machine originally imagined by him had been built immediately. The British would not have embittered the delay about their colleagues on the other side of the Atlantic. It was also during the season of ACE Turing began to explore the relationship between the computer and the mental processes by publishing an article, Computing Machinery and Intelligence, 1950, about the possibility of building machines that imitate the human brain function. Can a machine think, he wondered in his article. And in addition to focusing on the subject machine intelligence, Turing gained particular notoriety by trying to introduce, through this article, a test to decide if you really can or not a machine think imitating the man. In November 1991, the Boston Computer Museum held a competition among 8 programs to simulate the Turing test, won by a program called PC Therapist 3. The problem of Turing test is behaviorist nature, that is, only observes the outward behavior, which gives you a character somewhat reductionist. Serious disputes have occurred and still occur on this subject, which is beyond the scope of this book. Computer programming. Turing was also interested in the planning of operations of a computer, which then began to be called coding, regarding mathematical operations involved there, and began to write programming languages, then advanced to the hardware of the time. Turing was convinced that calculation operations were only one type of formal systems that could be imitated by computers. In particular, he noticed how the tables of his theoretical machine could become elements of an excellent grammar that would use machines to modify their Turing operations innovated to start drafting instruction tables, which automatically would convert decimal notation we are used to in binary digits. These could be read by machines that began to be built based on Boolean algebra. Turing foresaw so in the future, and programmers could work with the language now known as high level. He said, "The instruction tables should be made by mathematicians with expertise in computers and some ability to solve difficult problem solving. There will be enough work to be done such that all the known processes have to be converted in the form of instructions tables at any given time. This task will continue in parallel with the construction of the machine, to avoid delays at the end of this and the production of results. Delays may occur due to virtual unknown obstacles, to the point where it will be better to let the obstacles there than spend time designing something without problems. How many decades will take these things? This process of preparation of instructions tables will be fascinating." Turing's work in computing and mathematics was tragically ended by his suicide in June 1954 at the age of 42 years. Turing was gay, and after the escape of 2 British spies, the same trend for the Soviet Union in the early 1950s, there was a proper pressure on him to correct his condition through the use of hormones. Turing, not bearing the heavy pressure, took cyanide. Chapter 3. Technological Prehistory. As has been said, it was only possible to reach the computers by theoretical discoveries of men who, over the centuries, believed in the possibility of creating tools to enhance human intellectual capability, and devices to replace the most mechanical aspects of thinking man so. And always this concern manifested itself in building mechanisms to help both in arithmetical calculation processes as in repetitive or too simple tasks that could be replaced by animals or machines. This chapter will deal with the physical devices that preceded the computer, primarily analog machines that fueled the final race until the appearance of digital computers. Older devices. The first devices that have come to help the man to calculate have their origin lost in time. It is the case, for example, and abacus quadrant. The first, able to solve addition problems, subtraction, multiplication, and division up to 12 integers, and that probably existed in Babylon around the year 3000 BC. It was widely used by Egyptian civilizations, Greek, Chinese, and Roman, having been found in Japan at the end of World War II. The quadrant was an instrument for astronomical calculation, have existed for hundreds of years before becoming the subject of several improvements. The ancient Babylonians and Greeks, for example, Ptolemy, used various types of such devices to measure angles between stars, mainly having been developed from the 16th century in Europe. Another example is the industry bar for trigonometric calculations, used to determine the height for positioning the mouth of a cannon, which was developed from the 15th century. The ancient Greeks came to develop a kind of computer. In 1901, an old Greek boat was discovered on the island of Antikythera. Inside there was a device, now called Antikythera Mechanism, constituted by metal gears and pointers. As Derek J. de Sola Price, who in 1955 rebuilt along with his colleagues this machine, the Antikythera device is like a large astronomical clock without the part that regulates the movement, which uses mechanical devices to avoid tedious calculations. The discovery of this device, dating from the 1st century BC, was a total surprise, proving that some artesian Greek world Western Mediterranean was thinking regarding mechanization and mathematization time. Logarithms and the first mechanical computing devices. John Napier, Baron of Merchiston, is well known for the discovery of logarithms, but also spent much of his life inventing tools to help in arithmetic, especially for the use of its first logarithm table. From Napier, logarithms came another great invention developed by the brilliant mathematician William Oughtred and published in 1630, the slide rule. Won its current form by the year 1650, a rule that moves between two other fixed blocks, having been forgotten for 200 years, to become the 20th century the great symbol of technological advance, with extremely widespread use until be replaced by electronic calculators. With the development of the first mechanical devices for automatic calculation, effectively starts the technological aspects that will lead to the construction of the first computers. Preparing the way for the full automation of the calculation process was performed by the efforts of these early pioneers of computing, who saw the possibility of mechanization but did not have the tools and materials suitable to realize their projects. Among these big names cannot fail to mention Wilhelm Schickard, 1592 to 1635, and Pascal, as mentioned earlier, and Leibniz. There are works on these inventions, and only the primary element will be quoted, the made up, as many of these ideas will be present in some form in future computers. Almost all machines to perform mathematical calculations of these 3 centuries, from the 16th, had 6 basic elements in your configuration. A mechanism by which a number is entered into the machine. In the first project that was part of another mechanism, called selector, making it something independent in the most advanced machines. A mechanism that selects and provides the necessary movement to perform addition or subtraction of appropriate amounts in the registration mechanisms. A mechanism, typically some disks, that can be positioned to indicate the value of a number stored in the machine, also called register. A mechanism to spread goes 1 for all the digits of the register, if necessary, when one of the digits in a result register advances from 9 to 0. A mechanism to control function to check the positioning of all wheels after each addition cycle. A cleaning mechanism to prepare the register to store the value 0. Chapter 4. Architectures of Computers and Operating Systems. The term computer architecture is the ability to view a machine as a hierarchical set of levels that allows us to understand how computers are organized. The first digital computers, for instance, only had two levels. The first is called the level of the digital logic, formed by valves at the beginning and then by transistors, integrated circuits, etc. The second is called level 1, also called level microprogram, which is the level of machine language, where all programming was done by zeros and ones that would later be responsible for interpreting the level 2 instructions. With Maurice Wilkes in 1951 came another level, where the instructions were written in a more convenient way for human understanding. The technique was to replace each instruction of this new level of a set of instructions from the previous level, machine level, or examine one instruction at a time and perform the sequence of instructions equivalent machine level. Denominate these procedures for translation and interpretation 128. It simplifies the hardware, which now had only a minimal set of instructions, and thus fewer circuits were needed. After that, the evolution of hardware advances with the new scientific discoveries. Almost at the same time of appearance of transistors, for example, the concept arose data bus, which accelerated the speed of computers. At the same time appeared the major operating systems. Simply, an operating system is a set of programs maintained on the computer all the time, freeing the programmer related tasks directly with the operation of the machine, such as DOS and OS, IBM. These evolved, allowing new concepts that improve the performance of machines, such as the multi-programming systems, i.e., the ability to run multiple programs in parallel on the same machine. If one of these programs originates from a remote terminal, such a system will be called time-sharing. A significant milestone that allowed these advances was the introduction of input and output processors, also called channels. It motivated the appearance of competition concepts, communication, and synchronization. Since two processors are operating simultaneously, there is a need to provide mechanisms for synchronizing them and establish a communication channel between them. It is the era of mainframe architectures. Support for computational tasks and the development of applications are made in a central area called Computer Center. Terminals connected directly to the machine are only used by people related to the applications available. In the 70s came the supercomputers, machines that have innovated in architecture. To date, the growth efficiency of the computer was limited by technology, more specifically, for processing scalar requiring that the CPU of a computer to finish a task to begin taking another, producing the von Neumann bottleneck. A breakthrough came with the Cray-1 Supercomputer, the Cray research in 1971. It was the first pipeline machine, which processor an instruction executed by dividing it into parts, as in assembly line of a car. While the second part of the statement was being processed, the first part of another education began to be crafted. The subsequent evolution was called vector machine, or machine SIMD, single instruction multiple data, processors, which work with more than one dataset at the same time. A little later came the MIMD architecture, multiple instructions, multiple data, and appeared multiprocessor machines as the connection machine, with 65,536 processors. This technology also provided the advantage of working with existing 8-bit expansion cards on the market and relatively inexpensive 8-bit devices, such as controller chips. In the search for software, IBM was the digital research doors to see the ability to port your operating system, a great success. CP/M for architecture 8086, but this rejected the exclusive contract presented by IBM. So the IBM team headed for Microsoft Office, who hoped to get a version of BASIC, and ended up signing a contract not only this software, but also on the operating system. Microsoft acquired and increased an operating system 8086 from Seattle Computer Products, QDOS, licensing it to IBM, which began to market it with PCDOS name. The years of the 1980s could be characterized by software improvement, both operating systems and utilities, spreadsheets, text editors, and others, to the DOS standard, and the development of a market clones of different types of machines that would be able running programs designed to the standard. Apple continued to be satisfied with its Apple II family, although failing in the introduction of the Apple III and formidable Lisa, the first attempt to popularize the combination of mouse, windows, icons, and graphical user interface. But the price of $10,000 startled and amazed the market. The next step to be taken, not to mention the evolution and improvement of hardware without which it would not be possible, would be the gradual transition of applications for DOS environment, real C products, to a new environmental standard, which was beginning to take shape definitive, and starred in the beginning of a new age in the history of microcomputers, the Windows operating system, which has become the dominant standard for PC applications, making Microsoft a leader in defining multimedia specifications. It is important, however, to make justice. Windows' pattern inspired by the standard Macintosh, released by Apple in 1984, a computer that was able to offer more than a DOS prompt and a character-based interface. He could have multiple windows, drop-down menus, and mouse. Unfortunately, the Macintosh was not compatible with the programs and existing applications, and was not expandable. Computing as a science. Alongside this evolution of hardware and software, computer opened in range and new trends have emerged within it, incorporating these two entities. Artificial intelligence, theory of computational complexity, and database theory opened new fields of study. In the 1960s, computer science had become a true discipline. The first person to receive a title of PhD from a computer science department was Richard Wechselblatt at the University of Pennsylvania in 1965. They have consolidated the studies on the theory of automata and languages theory formal mainly with Noam Chomsky and Michael Rabin. The birth of the branch of formal specifications, which introduced a new paradigm in the development of computer systems, came in this decade, with the beginning of the search for the correctness of programs through the use of formal methods. W. R. Floyd, in 1967, proposed that the semantics of programming languages were defined independently of the specific processors intended that language. The definition can be given, according to Floyd, in terms of the method for test programs expressed in language. His work introduced what became known as the method of notes, assertive, inductive for verification test program, and one involving technical sets with sorting well-founded to prove the end of a program. An extension of Floyd's ideas was proposed by C. A. Hoare in 1969. Hoare made an axiomatic theory of programs that allows the application of the method of invariance Floyd programs texts expressed in programming languages, whose semantics is precisely formulated. This work has become even one of the foundations of what was later called structured programming. Dijkstra developed the idea that the definition, in the style proposed by Hoare, can be used for the derivation, synthesis of a program, and not just for your check. From these studies emerged software engineering, which aims to ensure the correctness in building systems. The development of computer systems so far was done in a way almost handmade. There was some criteria guidance during the process. This turned out to be fatal, as revealed certain studies developed in the 1970s on the development of systems. Lack of correctness and consistency, low quality, extremely costly maintenance because of problems not detected by the absence of a validation stricter requirements do not reuse code, implementation of missed deadlines as a result of errors detected over this same implementation phase, etc. Obeying a great deal of formalization, they appeared as a first reaction to this informal approach models and system development methods called structured, which actually are sets of rules and regulations that guide the various stages of system development and the transitions between them. It is the systematic approach. Yet here is not a formalism defined with precise rules. Prototyping and object orientation are approaches that can be considered systematic. The rigorous approach already has a formal linguistic system to document the development stages and strict rules for the transition from one stage to another. There is no requirement that the correctness of statements of changes made be made. Conclusion. The spread of computer literacy. When history look back and study the 20th century, among other things, you realize that, from a scientific point of view, they are characterized as times in which it produced a technological acceleration and a breakthrough in unprecedented communications. Not easy to find similar historical situations to technological expansion witnessed in these last 50 years of the century. After the Iron Revolution, electricity, petroleum, chemical, came the revolution supported in electronics and development of computers. From the 70s began the large-scale integration of television, telecommunications, and information technology, in a process that tends to set up integrated information networks with a communication matrix based on digital information, with great ability to serve data, photos, graphics, words, sounds, images, broadcast on various printed and audiovisual media. One can even say that, in a sense, the media are being suppressed because everything is becoming electronic. The integration of the media also generates a progressive fusion of the intellectual and industrial activities in the field of information. Journalists from newsrooms of major newspapers and news agencies, artists, student community, researchers are working on a computer screen. In some societies, such as the North American, for example, almost 50%, 1955 data, of the economically active population is dedicated to industrial, commercial, cultural, social, and informational related to collection, processing, and dissemination of information. There is an increased informational efficiency every day and cheapen increasingly technological costs. Not forgetting that the computer, unlike other machines, handling, processing, or transporting matter and energy, manipulates, transforms, and carries a much cleaner element and less consumer of energy and raw materials. It opens thus the door to a growth of almost unlimited information. Since you are dealing mainly in this book about the evolution of ideas and concepts that led to the emergence and development of computer science, we can now speak of a larger supra-concept, a result that computer helped catalyze: the emergence of the company information. Without wishing to enter the theme, worthy of a unique work and historical, anthropological, sociological, and even psychological implications that are beyond the present scope, two considerations will be made: the problem of excess information and the danger of impoverishment that can be caused by using improper computer.